This webinar will be consist of the two domains, where first we will introduce you the workflow of all the simulations, like what we can do in the EMIEMC applications. And I will start with introduction to Ansys, and then I will move to the electronics domain, where we will discuss the EMIEMC applications. And for this, we have two tools here for HFSS and SIwave. Before that, basically, many of you must be the new to the Ansys. So let me enlighten about the Ansys. Ansys is basically the leading software for simulation phases, where we provide simulations in the mechanical, CFD, semiconductor domains, and electronics also. So this is basically our product portfolio. So in this, you can see that each physics is covered. Whether I'm talking about material, like I want to choose before going to the simulations, I want to choose what material we should use. So for that, just give me a sec. Yeah, for that, we have a Granta tools. What Granta tools do is like choosing a material and any type of material analysis you want to do, you can do with the Granta tools. When we are moving to the sensors part, like I want to analyze the sensors and all, for that, we have a AB simulation tools. For system level simulations, we have a digital twin. There are multiple platforms here also, like cloud is there. Cloud is basically like you are doing some simulations and you want to analyze like how save proper data over somewhere, where after some time, if you want to use those data, you can use those from the cloud itself. OptiSlang is there. OptiSlang is basically for optimization tool. Like if you are just for example, if there is an RF engineer who is working on antenna part. So if you are going with this simulation and later you want to do the optimization analysis. So for that, we have a OptiSlang, and there's embedded tools also, SCADE. For safety analysis, we have maddening. So these three, here you can see that these three are basically our basically physics domain tools, which are basically structure is there for mechanical analysis. Like you want to do the shock analysis, vibration test, any type of test you want to do, you can do with the structure. When I'm talking about the fluid analysis, like you want to analyze any pump, or if there is some like a fluid flow you want to analyze. For that, we have a fluid tools here. CFD is there, Fluent is there, Forte, CFX. So for each these tools are for different applications. So similarly, we have tools for electronics also. In electronics, basically we have two domains. First one is low frequency and another one is high frequency. When I'm talking about the high frequency, it deals with PCBs or antennas, RF applications. If I'm going with some thermal part, all things are covered under the high frequency. When I'm talking about low frequency, it is basically for electric machines, motors, or any power electronics applications. So apart from these also, we have a semiconductor tools also. So if you want to analyze some IC chips, for that, we have a semiconductor tools. And these are the optics and photonics tools. Like if you want to go analysis of some lenses or lightning devices. So for that, we have optics and photonics tools. Discovery is there. Discovery is basically for 3D designing. It deals with like if you are like if you got some and like any model, whether I'm talking about the electronics, mechanical, or fluid, any models you want to do the analysis part, you can do that in the discovery. So this is basic workflow, and this is basic product portfolio of all my like our Ansys tool. So in case, and there is one more thing for each applications, like whether talking about the structure, in a structure itself, we are talking about the LS sign for each applications, we have a different technical experts who deals with like if you are talking about the mechanical part. So for mechanical, we have a different technical expert. For LS we have For fluid, we have for electronics, there are different technical experts who deals with this physics. And in between, if you have any questions, you can directly write in the chat box, or you can ask also. In between the presentation, if you have any queries, you can ask. So when I'm talking about the electronics is basically, there is a one quote it tells that electronics does not make any industry, but electronics is part of every industry. Whether I'm talking about the networking and in networking domain, also we provide Ansys electronics to suits. Wireless is there. Industrial equipments, I'm talking about in industrial equipments, also we use electronics. In aerospace and defense, in semiconductor, in computing devices, oil and gas, automotive, biomedical, you must have heard SAR analysis, which is basically specific absorption rate. So that type of analysis is also possible in HFSS and SIwave. Now I will move to the electronics tools. So these are the electronics tools which I was talking about. HFSS is there. HFSS basically consists of three interfaces. First one is HFSS 3D modeler. HFSS 3D modeler basically deals with when I'm talking about some RF applications, or I want to do the system level simulations. So for that, we will need the HFSS. Just for example, you want to design an antenna, and after designing, you want to place that antenna over somewhere. If you are a road industry, if you are a EV industry, so you can place those design antenna over that model and analyze how it is interfering with other components. So for that, we will use HFSS. It is it uses FEM solver, and there are multiple more solvers we can use in HFSS according to your complexity. So there is an integral equation solver, there is a SBR plus solver. SBR plus solver is basically for antenna placement part. And later we have a Maxwell. Maxwell is basically for low frequency applications. So when I'm talking about designing an electric machine, or I want to do some low frequency level application, power electronics applications. So for that, we have Ansys Maxwell. SIwave is totally dedicated tool for PCBs. So first I want to confirm here that we don't design PCB here, we simulate it. For simulation of PCB, we will go with the Ansys SIwave, where we can do signal integrity analysis, power integrity analysis. I want to do the EMIEMC application analysis. For all these applications, we will use Ansys SIwave. Now, Ansys iSpec is there. iSpec is basically for thermal applications. Just for example, I have analyzed a PCB in the SIwave. Now I want to see how the temperature is distributed over all our PCB. So for that, we will couple this SIwave with the iSpec. And this type of simulation is called co-simulation, which is basically coupling one tool with the other tool. If you are doing some simulation with the HFSS, so you can couple HFSS with the iSpec, you can couple SIwave with the iSpec, or you can couple SIwave with the HFSS also for the circuit simulation. So Ansys provides this, you don't need any other tools for different applications. You can directly couple these two tools, which will automatically extract those data from the other tools and use it as an input in the next tool. So now Q3D extractor is there. Q3D extractor is basically for RLGC extraction parameters. If you there is some PCB. Now I want to extract the RLGC parameters from the PCB. So for that application, we will use the Ansys Q3D extractor. MotorCAD is there. MotorCAD is basically low frequency application. So what MotorCAD provides is it is basically for motor designing. So I want to design a motor, but I have some particular data and I want to analyze how the rotation is there, rotatory is there, and how this will apply in the physical words. So for that applications, we will use the Ansys MotorCAD. Next, we have a EMI3D cable. EMI3D cable is basically for I will just explain this with one example. like there is an EV industry. So there is a cable installed in a car to analyze how the radiation is going on through the cable and how the what are the how this cable is interfering with the other component itself in the car. So like there is a multiple components in the car. So for that applications we will use a EMI3D cable, and cable harness, wire harness, these type of applications are also possible in EMI3D cable. So this was basically a brief intro about our electronics tools. So these are the key tools which we will use for different applications. So like when I talk about the HFSS, it is basically primary application for the HFSS is basically RF applications, antenna designing, antenna placement, and after placement of antenna, how it is interacting with nearby devices or nearby components, whatever they are. So for that, we'll use HFSS. HFSS has no limitations. Like if you are designing some, like just for example, if you have designed some model in the SolidWorks, some other tools, other CAD tools, so you can import all those data itself in the HFSS. Same with the SIwave. If you are like, just for example, if you are using a LTM tool, or you are using some KiCad or here any tool your cadence you are using for the PCB designing, so you can import those all design models in SIwave. So now I will move to the SIwave part. So as today we are covering only about the electronics. So if you have any queries on these any tools, you can directly mail me or you can contact me. I will let you know any applications if you like, if you want to explore more about HFSS, if you want to explore more about Maxwell or MotorCAD or EMI3D cable, so you can directly contact me. So SIwave is basically a dedicated tool for PCBs. So now after designing the PCB, basic problem arises like what are the signal integrity issues, crosstalk analysis I want to do, whether the nets are properly working or not, whether each component's distance is like the distance between the each component is perfect or efficient or not. So for that and all these analysis are possible itself in the SIwave. So now here you can see that this after importing your PCB in our tool, it will look like this. And like basic question arises from all the customers, like uh, whether I'm importing the data. So whether I need to import each component separately or all the data will be extracted itself from the PCB file. So yes, if you are importing the EDB, or like there are the multiple formats there, like ODB plus plus, or where I'm talking about EDB format, or there are multiple formats. So ODB plus plus extraction is basically most suitable for this. So when you're importing that file, you are basically importing the library you are importing here. So all the components in the PCB will be imported itself in the SIwave. So now this is basically what a few applications where where we use SIwave for for crosstalk analysis, for impedance analysis. So this is basically there are the two domains, frequency domain and time domain. When I'm talking about the frequency domain, we will analyze with how much like whether the how much percentage failure is there, how much percentage passing is there. And when I'm talking about the frequency domain, sorry, time domain, so I will go with like this. Here you can see that this red zone is basically our failure zone, and this green zone is passing zone, and this orange zone here you can see that orange nets, these are basically our warning zones. So our warning zones tells you that this might go to the failure after few years. And calculating the lifespan of a PCB. So for that, just a sec. So in mechanical section, I have shown you one of the tool here, Shadlock. Shadlock is basically for calculating the lifespan of the tool. Any component you have, you can predict the lifespan, like how much time it will work. So for that, we can use Shadlock. This is basically for reliability testings. So here, when I'm talking about we can plot the coupling plots, we can do the 3D interactive bar graphs, we can plot near or far voltages, or we can plot the coupling coefficients also. So here you can see that this is basically near field analysis. In near field visualization, you can see that this is how it is plotted. And this blue zone is totally safe zone. Green zone is also safe zone. And this red zone is our failure zones. So it tells us that here the radiation, near fields are higher and the emissions and noises are there higher. So, and this is our far field analysis. So basically, when I talk about the near field and far field, near field is basically our conducted emission test, and far field is basically our radiated emission test. So accordingly, there are the four reliability tests. First one is our signal integrity. Signal integrity is basically like when, just for example, I am transmitting a 0 1 signal, and at the receiver end, I am receiving 1 1. So this is basically in between, there is a loss in the signals. So for that, we will do the signal integrity analysis. Power integrity is basically maintaining your power, like how, like just for example, I'm giving some 3 watt power to our receiver, but our device is not that much compatible to accept those power, so it will burn. So for that analysis, we will do the power integrity analysis. So now our today's agenda is basically on the EMIEMC part. EMIEMC is basically like interference type of things. Like there are some devices nearby. So how those are interfering with each other. So for that, we'll do the EMIEMC test. So now after that, these three are possible in SIwave, and but for thermal integrity application, we will move to the ice pack simulation. Basically, this tells us what is our signal integrity analysis. So there is a transmitter, there is a receiver. So what transmitter do? Transmitter transmits a signal and receiver receives. But in between, what is their interference and what type of signals are lost and all. So for that, we will do the signal integrity analysis. And these are the some signal integrity issues we face, like impedance mismatch, there's a crosstalk, or whether I'm talking about the delay, attenuation, reflection, emission, jitter, ground bounce or load impedance. So all these things are possible itself in the SI wave. SI wave deals with all type of from the basic level to the advanced level. We can do all these simulations. So yeah, you can see that there's a chip, package, PCB, and memory. So for that, first mode is like write mode and second is read mode. So in the write mode, we will analyze how this whole issue is there. And at the read mode, we will again take a feedback. So take a feedback like how it is there, proper analysis is there or not. So these are the some of the results we will generate after completing the simulations. So SYZ simulations, we can do the SYZ. In the SYZ, we will calculate the return loss, transient loss, all these type of analysis we can do the SYZ simulations. Full wave resonance test we can do, power and ground bounds, time domain reflectory, and near field radiations. So this is how our full board analysis is there. Like for this is basically for time domain crosstalk analysis. So this tells us that there is a dip here. So with the help of this dip, I can analyze from this range. Here you can see that this is the range we have defined. So if this range tells us that how the cross like interference of the crosstalk is there. And this tells you about the failure parts. So with this data tables, I can analyze at which nets we are our violation is there. So just a sec, I will just zoom it a little bit. So you can see that this is our flexed violations. These all the green nets are basically our passing nets. So there is no violations in these. So from this, you can see that there's a this I already showed you. Like these green phases are basically our passing zones. This red zones are our failing zones, and this our orange zone are warning zones. So apart from this, SIwave deals with various applications. So like DC analysis, you want to do the power delivery PD analysis, or you want to do the AC frequency sweep, or electrothermal or mechanical analysis. Like sometimes what happens is when I'm dealing with some PCB, so everything look fine. Like I have completed my PCB simulations and there is some, like I have suppressed the signal integrity issues. There's a no power integrity application needed. After that also we face some problems. So for that we will do the electrothermal analysis. So what electrothermal analysis will do is like it will couple your EM data with the thermal data. Like if you have accepted the SYZ parameter return loss and all. So after completing that, we will move to the thermal part. We will generate the temperature, like which component basically in when I'm talking about the PCBs and all, here the few components are there like ISBTs or MOSFETs. So they produce more heat. To analyze those analysis, we will again couple this SI wave with the ice pack, and this process is basically like electrothermal analysis. And just for other applications, like if you want to couple your SIwave with the mechanical analysis, you can do that also. HPC applications, HPC is basically like, just for example, your complexity is much more. So with increase in the complexity, the time also increases. So to reduce the time of that simulation, so we will need a HPC license. So for HPC license, basically what we do is we like just for example, you have a PC, it automatically Ansys uses 4 cores. 4 core of your PCB will sorry, 4 core of your PC will be used. But if you want to increase those cores, you will need the HPC. HPC will increase your cores from 2 ka power n. Basically, like when if you're using one HPC license, you will move to the 8 cores. If you're using 2 license, it will use 16, 32, and move from that. PI advisor is a PI advisor basically deals with like if you are using some resistors of, just for example, if you are using some resistor of Samsung model. So apart, like if you want to use some other models also, you can directly extract those from our library and you can use that. Electromagnetic and EMI scanner is there for this EMIEMC applications. So EMI scanner directly provides you a workflow. So workflow is itself inbuilt there. So you can just choose the nets and again move to the simulation part and it will automatically generate the results. So these are the some of the examples which we have performed in the SIwave. So first one is basically we have done a voltage drop test on a PCB. So you can see that this from this graph. So these values tells us that at each nets what is the voltage drop. So from red zones are higher zones, and again accordingly this. So this is basically our excessive current. So now sometimes due to the excess of currents also we face many problems. To analyze this also, we can plot it on the SI wave. So there is a current plot we have plotted on our PCB, and this is our eye diagram. Eye diagram basically tells you that how much radiation is there. Like just for example, there is one like we have when we open our eyes wider. So it like it's more visible, like whole area is visible. But when we are closing the eyes, so visibility is decreasing. So similarly in the eye diagram also, when this is wider, it will basically there will be the more radiations, and when it is closing or the little bit low, so there will be the less radiations. So now this was all about the SI wave. Now I will move to the EMIEMC applications. So from like EMIEMC deals with each type of analysis you want to do, from chips to the system. Whatever you want to do, you can do that in the our Ansys SIwave plus HFSS tools. So when we are doing with like some some misconception here ki, like you if you are doing the simulation, you don't need to do the physical testings. So this is totally false. You have to do the physical testings. What simulation is doing here is it is reducing the number of iterations you are performing in that test. Like if you are performing some number of eight, if you are getting your results in the eight number of iterations or six iterations, you will get those results in one or two iterations. So it will automatically reduce the costing. For each test, you have to charge differently. Like for each number of tests, you have to charge. So for that also, it will automatically reduce. And one more thing is like designing cost is also decreased. Like if there's a basic workflow in the physical test, you design your model and after designing, you move to the testing part. And if you face some failure or some errors, you have to again move to the designing phase. What simulation will do is simulation will give you before going to the designing phase, just do import those whole models itself in the our like virtual model in our tool and analyze what problems we can face later. So for that also we can like there is a cost reductions and test reduction both in the using the simulation. So this is basically our workbench, like how the test is like there's some pre-compliance test and moving to the anapneic chamber, then do the full platform test. So this is whole possible in itself in the our Ansys tool. You have to just import the first bench test, then import the anatomic chamber, then again perform the full test, full platform test. So now these are the some applications where EMIEMC applications is applicable. So just for example, there's a like a full vehicle. So you want to analyze the emissions or system analysis of those vehicles. So you can do that itself in our EMIEMC. So like if you want to analyze radiations through the cables, or you want to do the analysis, crosstalk or shielding effects through the cables. So for that also, with the applications of wiring harness, you can do that in the EMC Plus tool. Easy applications are there, like radiated emission test or conducted emission test you want to perform, or bulk injection, or any other EMC standard test you want to perform, you can perform. So now antennas applications, like there are, just for example, there are the two vehicles going nearby. In the graph, in the diagram, you can see here. So there is a one antenna installed on one vehicle, and there is another antenna installed on the another vehicle. So how much distance like this antenna can interfere with this antenna to proper placement, like at which place we can place this antenna so that there will be less interference or no interference. So for that also we will go with the HFSS tool. SAR analysis we can do like there is a like we are using a mobile and there is a radiation coming from the mobile. So how much radiation our body can absorb? So for that also we can do that various tests. So these are some other simulation capabilities, so which will like enhance our EMC analysis. So for PCB or component level simulations, we can do for cable harness, for antennas, for electromagnetic exposure to the body, or for full platform simulations also. Just for like when we're talking about the PCB or component level simulations. So in this, what problem we usually face is high speed routings. Like when I'm talking about the connector designs, like at particular how the connectors will be connected so that there will be less interference, or there is switching circuit or switching regulators there. So how those things we can compile with our whole system so that there will be less interference, and these are the some Yeah, hello. Is there any query? Hello.
Yeah, Shubhendra, I don't think
Yeah,
there's any query. You can continue.
okay, sure.
Thank you.
So like for these engineering challenges, we have a different Ansys capabilities here. We can do circuit simulation to analyze the switching regulators and filtering components. So the parasitic extractions, for that we can use our our tool Q3D extractor. For near field or far field EMI applications, these are the different capabilities which Ansys provides, and these are the different outputs we can generate after for these any challenges. So we can generate rule violations, which I have shown in the previous slides. So like they are the what are the violations there, and for we can plot electric and magnetic fields. We can plot as parameter analysis. We can plot radiation plots. We can plot emission graphs and all. So when I'm talking about the cable harness, so in the cable harness problems, so basically what challenges basically we face is crosstalk analysis. So now crosstalk is basically like I will explain crosstalk with just one example. Like there is a mobile placed under the TV. Okay, so when we receive any call, so there is a dispute in the signals. So this is basically due to the crosstalk. So there's a radiation problems there, like cable is radiating some signals. So how this radiation is affecting other component itself in the vehicles or any like your model. So for that also we can do the radiation analysis. Susceptibility is there. Susceptibility is basically like there is some emissions there. Like just for example, there is some leakage or there is some plane wave analysis. So for that type of analysis also we can do. And for these, we have a different analysis capabilities. We can streamline cable workflow. Like we have a proper workflow for the cable analysis. We have a simulation for the complex structures. Like just for example, there's a plane or aeroplane or there is some satellite or anything. So there is a cable installed in those components also. So for that also we can do that for consideration of all cables in our in one platform. Like for there is a EMC plus tools which deals with the cable harness part. So we can do that self in the our our tools. So what from what outputs we can minimize, like we can see that these problems are resolved. So we can induce some induced voltage, like we can induce some like voltage. We can see the current, we can see the radiated field or shielding effectiveness. So these things tells you that how these problems are resolved. So antenna part I already shown you, like that some, just for example in this diagram you can see that there are the multiple antennas itself in one car. So how each antenna, like there's a KEC receiver, there's a printed antennas here, there is an TMPC antenna, TPMS antenna, there's a second TPMS antenna. So these are all the antennas itself in one environment. So there must be interference here. Like this must be interfering with this, or this must be interfering with this. So to analyze this, what should be the proper placement of antenna, like how much distance we should keep between those two antennas. So this thing is possible itself in Ansys, and we can do this by the full electromagnetic field coupling solvers, or we have a one more tool which is basically our toolkit. Emit is there, which will help you to analyze this proper placement of antennas. So how we can resolve, like how we can see that if we are increasing the placement or if we are decreasing the placements of like distance between the two antennas. So how we can realize like this is a proper placement, like how we can see we have taken some distance between these two antennas. So did this when we will import this in the physical world, so I will face no problem. So for that, we will first plot E or H fields. We will plot S parameter reports. We will plot radiation plots. So this tells you that your problem is resolved. So when I'm talking about the human body model, so here you can see that just there is a one guy here who is using a mobile in the attaching it from the our ears. So there is a radiation which is going through coming from the device, and it is absorbed by our body. So we have to analyze like at particularly what is a maximum radiations our body can absorb. So for that we will do the SAR analysis. We will plot the field distribution in the large models. We can also do that. We can plot the field distribution on the large models, like there is a ship or there are some bigger models. So for that also we can analyze, and we can directly plot the surface field plot, and we can analyze our problem is resolved. And when we're talking about the full platform simulations, so now I was talking about at the component level, or I am talking about some body level. So now there is, just for example, there is a room, there is a chamber. So in this, there are multiple, like there is a one PC here, there is a one mobile, there is some laptops, or there is some TV. So these all components are radiating some signals. So in this whole environment, how our simulation will work, it will be designed to the full platform simulations. So here you can see that just for yeah, we have a car. In this car, we have a electric transaction motors, we have a DC-DC converter, we have a controller, we have a thermal system, we have a battery, transmitter, transmissions, charging ports, trajectory, battery packs. So there's a multiple component itself in our one car. So from this we can analyze each component should be properly placed, and each component should like limit its radiations and interferences. To analyze this, we have done a conducted emission test here. You can see that this is our conducted emission plot. So in this level, so for each components we have plotted, and it is how interference is there we can analyze. And this is our radiated emission. Radiated emission basically like just for example, there is a car. Now at some distance there is a cable, or there is some substation. So how that substation is also affecting our body, so we can analyze through radiated emission test. So for electromagnetic simulations, so this is basically our real product. There's a key, car key. So when we are moving to the simulation phases, this will like inside this will look like this is a PCB here. So how it will look here. Now, when I'm moving it to our simulation tool, it will look like this. So you can see that all the components are visible, and each component, how each component is producing heat or radiation field, each things will be analyzed through our tool Ansys tools. So now sometimes we faces some problems with the calculating the inputs. So totally inputs depend, accuracy depends on the inputs we provide. So, but sometimes we have some resistors which we have purchased from local vendors. Okay, so we don't have the data for that resistors or that capacitors. So we have a 3D component library where you can use the resistors and all. You can provide particular like value, parameter value, and you can use that for your model. So this is basically our full wave simulation which we are doing. But this is a battery. We have imported the circuit of the battery. For the cable, there's a bus bar, DC bus, inverter. There's a variable voltage or frequency sources. There's a cable installed. So this is whole circuit simulation we will do itself in our Ansys circuit. So now for each CISPR level, we have a different limit lines, which will be imported through our limit exceptions. And after that, we will analyze what is the violations there. So here you can see that there is a one gearbox. So in this gearbox, we have plotted the current which is induced from the interferences. So we have, you can see that we have plotted the currents induced on the gearbox. So here you can see this is a magnetic field analysis. So this is our red zones where we are getting approximately 875 ampere per meter values. So in this, you can see that this is basically for both applications we have done. So this tells us that how we can plot the current and analyze our simulations. So our output will look like this. These are the multiple tests which we have performed. So these are the multiple tests which we have performed. This is basically bulk injection which we have performed in our SIwave. We have a radiated emission, we have a electrostatic discharge, we have an MP test, we have a conducted emission. So there is a broad applications which we cover, and each things we can analyze through our tools. So now I will move to our case studies which we have performed for various customers. So this is basically one of the case study which we have performed for Rockwell Automations. So in this, what we have done is we have like this is two modes. One is differential mode and another is conducted common mode. So in common mode, here you can see that this black part is our simulated results and this red part is our measured result, which are provided by the customers. So we have done that for that, and here you can see that from this we can analyze how measurement result is varying with the simulated results. So same with the differential mode. And in this, you can see that we have provided a limit line here. So this limit line tells above this limit line, if there is something above this limit line, if there is some simulations or there's some noise. So these noises are affecting or interfering, are basically interfering. So these noises will not be considered. So limit line basically provides how much like accuracy or like how much perfect your interference is there. EMIEMC applications are we are performing. This basically conducted emission test. In this here you can see that this is basically a workflow. There is an EUT, there is an LISN, there's a vertical ground here. So first step will be we will import the board file. Again, move to the load extractions. Then do the system simulations, and after completing the system simulation, we will analyze the noise, and if there's any noise, we'll again move to the system simulations. So this is one of the radiated emission tests. So here what like conducted emission was basically near field analysis, and when I talk about the radiated emission, it is basically like there is some EUT and at some distance there is an antenna placed, which is like, so now we have to realize how this antenna is affecting this EUT. For that we will do the radiated emission test. So this is basically our anechoic chamber because it absorbs the light radiations. So this we have done here. You can see that this case study we have done for GAMCO. So they have given the measurement results, how much noises they are getting. They told us that we are using a antenna over 3 meter distance. So now tell us like how much accurate your software is with the simulation results. Now you can see approximately the simulation results is very like accurate with the measurement results. This tells us the accuracy of our software. So this one was electrostatic discharge method. In this, there are the two conditions. First condition is when PCB is not connected to the galvanic meter. And when second situation is when PCB is connected to the galvanic body to one to two PCBs to another two PCBs. So when this situation, in the first situation, it is basically not grounding situation. In this, we can see that there is a noise here. We can see that noise is here. And when we are doing the grounding situation, noise is suppressed. So this tells us that how we can suppress those noises, and this is our proper setup. In this, you can see there is a ESD gun. Now, from this ESD gun, we are incidenting a plane wave on this our UT. So for each applications, for first applications and for the second applications, we will analyze the noise after this. I'm putting this ESD gun, those RF signals over our UT. So this is basically a conducted RF unity test. In this, like we analyze that there are the 4 critical points we have to work on. So now I want to analyze at each time how voltage is varying. So for that, we will incident a plane wave on these 4 critical points. And after that, we will analyze how much voltage is varying with respect to time for each 4 points. So from with this, we can analyze the cause of our interference, and we can analyze at which time or at which particular time we are facing the problems. So now RF immunity test is there. Our RF immunity basically like when in the radiated emission test, that device was like the antenna is in the stationary position. But when I talk about the radiated immunity part, device will not be stationary, it will move. So when this, like just for example, this is our UT, this is our antenna. So I'm just giving an example, it is not basically like that. So when the distance between these two are increasing, voltages here, you can see that varying. For that type of analysis, we will do the radiated immunity test. So this is basically our workflow for the simulation. So in this, first is our PCB level simulation, and this is our system level simulations. So for PCB level simulation, first we will import the PCB file from any software you want. If you're using CAD and Ceregro, or you are using Mentor Expenditure, or you are using Zuken, or you are using LTM. So you can import these data in the SIwave, do the full wave simulation. After doing the full wave simulation, we will extract the S parameter results. And after extracting those S parameter results, we will move to the circuit simulations. So in the circuit simulation, we will generate the radiated emission, conducted emission plot. And after that, we can move to the field plot. And where we can generate, like again move to the SIwave, and we can do the whatever, like after doing the push excitation, all the data from the circuit will be transferred to the SIwave, and we can plot the near field or far field here. So this was basically a simple workflow how the EMIEMC works. Now when I'm talking about the PCB level simulations, so these are like first step we have performed in the SIwave, importing the files, assigning the S parameter, if there's some data you want to add, you can add. After that, we will create a port. We will do the SYZ simulations, well as a return loss, then move to the circuit simulation. This phase is basically our circuit simulations. We will import the PCB blocks in the circuit. Again, do like assigning the, if you are like spice model for the, if you have spice model, the resistor, capacitor, anything, you can import that, make the connections. And after that, we will do the transient analysis. Here you will get the conducted emission plot itself in the circuit. And when you will excite the data from the circuit to SIwave, you will get your far field radiated emission plot in the SIwave. So this is basically our workflow for our PCB level simulations. So what inputs you will require? You will require a PCB layout file, PCB stack up details, our circuit schematic, your project BOM file. BOM file basically deals with like if you have some components missing, so you can import those from the BOM files. You have measurement standards, you have a limit line. So these are the basic inputs required. And after that, you will get these two outputs, conducted emission, radiated emission plots. So This was basically for PCB level simulation. When I'm talking about the whole system level simulations, so for that we have a different system integrations. There is battery, there is cable, there is a motor. So what we will do is we will import each circuit of each components. We will import the source model. We will import circuit of a drive-in model, cable model, motor model, and integrate it itself in the circuit and generate the radial transmission plot. So this is basically how your like there's a car. So in this car, there is an antenna, there's a battery, there's a motor, there's an inverter. So we will import all the data here. There's a battery, for cable, for motors, for antennas, and we will connect it with our whole model. And after that, we will generate our results, whatever results we want. If you want to generate the conductor dimension plots, you can generate here. If you want to see how much voltage is plotting over the PC and our antenna voltage, how much voltage induced in the antenna, so you can do that also. So for testing chambers also, you can go with the simulations parts. Like this is basically, this deals with the radial dimension plots. When you want to do, there is an LIS and there is a simulated load, there is UT. You can do that. You can directly link your data with the SIwave, and you can generate the radial dimension plots. So now when for CISPER 25 model or any CISPER model you want to code, this is our physical testings. We will design system design, we will equipment of the PCB design, we'll again move to the performance testing, then move to the equipment testing. But in when we are using the PCB design workflow, so what we'll do is these three will be common, and after that CISPER 25 environment will be installed with the PCB. Like PCB will be attached with the whole system, and you can analyze how that PCB is and interacting with other components. So radial dimension workflow is there. In this, there's some near field analysis we have generated first, and after that we will move to the generate the our radial emission plots. So this is basically our circuit schematic. So there's a source here, power source. So there's a load and there's a clock. So now we can also analyze the delay. We can analyze what is the interference is there. So all things we can do itself in one tool. So this is whole circuit which is imported here, and after that we will some space is needed or anything, you can analyze through our circuit simulations. You can plot voltages or field plot also. If you want to apart from plotting the radiator emission of far field emissions, you can plot other things also here. So in basic, in the physical prototype, you can do passing or failure reports. And when you are moving to the physical prototype, you need a passing or failure report, like how much passing is there, how much failure is there. But in the virtual prototype, you can troubleshoot your problems. If you are facing if you are somewhere you are failing, you can again troubleshoot it and you can work on that. So this tells what is EMC simulations, why EMC simulation is needed. So this was basically EMIEMC applications. So if you have any queries on this, you can ask. We will move to the thermal part. I will just give you a brief intro about thermal. I will not go in detail because we usually conduct these webinars for each applications. So we have performed for RF applications. We have done the webinar on the RF applications. We have done the webinar on the PCB level simulations like signal integrity, power integrals. So today's our agenda was basically for EMIEMC applications. So I will just brief you a little bit about ATM applications for thermal applications. So in this, what we do is basically we analyze from chip level to the superconductor level how temperature or airflow is there. So we can do that itself in our electron cooling applications. Like we can couple our DCIR simulation results with the thermal results. Like where we have plotted our PCB here. This is our PCB. Now I want to move to the PCB levels thermal simulations. So I can directly couple. This is our GUI for SIwave. So like we have completed the simulation of the PCB in the SIwave. Now I want to directly couple those data with the iSpec. I can directly couple it with the iSpec. And after coupling it, how it will look like this. Like this green zone is our moderate temperatures. This is red zones are higher temperatures. So we can analyze those data also. So these are the some of the applications which we have performed in our iSpec tool. So we have performed heat sink fan assembly. We have performed thermal conductivity map on the PCB. We have done the velocity vectors. Just a sec. We have done the velocity vectors we have plotted, and we have done for the whole data centers also. So this was basically our presentation part. So now if you have any queries, you can ask. Anyone? Just a sec.
If anybody has any questions, you can please put it in chat box, please.
Yeah, you can you can do the EMC test, EMIEMC test in software. Can you just do PCB? Yeah, I will just I'm just going through that. I will just do when I'm I will do in the software. But before that, I want to know if any queries on this part, presentation part. I will show you one of the simulation I have done so far in the SIwave. Okay, so I think there's no query, so I will move to the simulation part. So for that, first we need
there is a one question. So,
yeah,
like, is it also possible for EMC application, the testing and simulation for microcontrollers?
yeah, it is
Arduino,
possible for
the Arduino
microcontrollers.
Nano.
Yeah,
So
yeah, you
they are
can
the
do
same
that.
part of the PC band, all right?
Yeah, yeah, you can do that itself in our SIwave tool. Or if you are doing for the system level, you can do that in the HFSS.
Acha, okay, fine.
Yeah.
But is like all the Arduino or the microcontrollers, they are not a commercial viable in vehicles, right? In automobiles, they don't use that one. So we have to make our own custom PCBs.
Yeah, you have to make your own custom PCB. For that, you have to use some other tools. Designing is not possible here.
Okay, so it is only the simulation part, right?
Yeah, it is only the simulation
Yeah,
part.
and what about like VCU, like controllers? We can analysis over here, right?
Yeah, you can do that. If you are going with just controller simulation, you can do that in the Maxwell also.
Okay.
Not about
And
apart from the
what about
apart
the
from the
controllers for
EMIEMC
electric
applications.
vehicles?
Yeah, EV vehicles applications are there for we have different tools also. Like currently, Ansys is collaborated with the Ansys is now a part of Synopsys. So we for EV applications we have EV tools there also, which are basically available in our product portfolio. So for you can use those tools also, or otherwise you can directly couple this from the our HFSS and you can use those also. Like in HFSS also there are the multiple. These are the multiple vehicles itself in our component library. Like there's some Mercedes model, there are some Audi models. So you can use those also for your like not for your project, but for your understanding, you can use those.
Okay, and is there any available for the two-wheelers like Ether controller or the Ola Ether with like ultraviolet?
Yeah, yeah, HFSS is there, no? And in HFSS, you can perform any type of vehicle simulation you want to do.
Okay, fine. Yes. Thank you, sir. Thank you.
Okay. Yeah, Tusharji, for like when we are going with the motors, generators, diode integration, we have a tool called Maxwell and this MotorCAD. These two tools you can use for the mathematical models. So Tusharji, is it clear? So anyone else? If you have any queries, you can ask right now. No, basically Maxwell and MotorCAD basically deals with these two tools are basically part of one domain. These are basically an interface just for example, I have shown you here different tools. So for like when you're talking about the motors, generators, diode integration, these are itself possible in the Maxwell itself. You don't need different tools for these. But when we are moving to the thermal part or you want to do the EMIEMC testings, you will need other tools. You can couple those tools, like both the tools, and you can use those. Is it clear? And in detail, Tusharji, if you need yes, you can do that itself in the side like Maxwell. Okay, so I think there's no more queries. So I will move to our demo part. So just give me a sec. So this is basically our Ansys SIwave. So now here you can see that you can import any type of files you want. Like if you want to import the ODB plus files, or you want to import some DXF files or Ansys EDB files, you can import those files. So as I have already done here, so I will just open my model here. So this is how PCB will look like when I'm importing the model from any like ODB plus files or other things. So our first step will be verification step, like whether the translation is successful or not. So for that, before that, I will just let you know that other import files also, you can directly go to the import. You can import if you are importing some IPC, ODB++, or Mentor, if you're using Mentor expansion designs, you can import those also. And in case if you are using LTM, so for that, the best process is ENF files you can import here. So doing that, going verification phases. So now I will first verify the stack up details. So you can see that these are all the nets available. So this is basically top net, ground nets, and what are the materials used in these nets also. Yeah, you can accept those. After that, just click OK. And when the green tick will appear here, beside the here you can see the green tick is in. Now stack up verification is done. Now I will pad stacks I will verify. So these are all the pad stack with proper data what are the material used, what is the distance between the absolute distance. So now what is safe for that? You can edit those also here also. If you are like, if you want to increase the radius of this our pad stack, you can from this you can increase the absolute distance. You can increase the radius of the pad stack. If you want to like change the shape also, you can change the shape also. Click OK. Then again move to the circuit element parameters. Now I will verify whether my all the components are properly imported here or not. So first one is there, you can see the capacitor. These are the 9 capacitors. Not all the 9 capacitors are active. We have a 4 inductors in our this PCB. We have a no resistor. We have a 31 ports. We have no voltage probes, we have no current source, we have no voltage source, and we have no net terminals. So we click OK. After that, we will analyze the power and ground nets. So what power and ground nets will we do? It will basically tells you that at what particular points we will do the power applications. So these are the power and ground nets. If you want to move some nets up, like if you there are some power non-power ground nets you want to use at a power ground nets. So for that also you can directly drop down them and you can make them as a power of ground nets. Now after that we will sanitize our model. So we will click all these components, check whether they are matching nets or not. Like sometimes during the translation, what happens is like there are some multiple matching nets imported. So for that, we will do the sanitization and clicking on sanitization. All these things like matching nets and all will be deleted. And clicking OK. Now close this, and from there you can see that all the data. This is our power and ground nets level. This is our extended nets. This is our differential nets. And this is our component files. Just a sec. Yeah. So in this, you can directly see what are all the components here. Okay. So now before going to the simulation field, first I need to verify whether there is like the verification we have done is perfect or not. So for that, we will click on the validation check. We can check whatever we want, like if you want to interacting polygons, or there's some disjoint net, or there's some DC sort errors. So for that, we can increase the cores according to your complexity. If there is a more complex design, you can use more cores. If you have HPC license, you can use up to 32 or 8 cores, 16 cores, whatever cores you want. So clicking on the OK, you can see that simulation is running. So you can see there is no error right now. So in case if there is some error, there is an auto fix also. It will from the system, it will automatically generate and it will fix your problem. Okay, now our next step will be creating the pin groups. So for creating pin groups, like when we are creating the ports, before that we have to create a group of pins. So for that, we will just for example, there's an input ports. So I will click in this. I will check on this J1 part. Go to the Home tab. So go to the Tool tab. And here you can see the Create and Manage Pin Group. Click here. And clicking on any components, you can directly create or generate the pin groups. Whatever components you want to choose here from nets, you can choose and create a pin group of those nets. So this basically helps you to create the port. Clicking on the Control D, it will automatically fit your design itself in the SIwave tool. And after that, we will generate the ports. So generating the ports is basically two two methods. First one is automatic method, like it will automatically generate a port. So click on generate ports, choose the part number, like part name, whichever part, and reference destinations. Like I want to create a port on the J1. Click on the J1. First, choose the positive terminal. Clicking on the positive terminal, I am choosing P12V as a positive terminal and ground as a reference terminal. Clicking on that, just here you can see the port, and just click on the create. It will automatically create the port. And later you have to again generate all those, like for other ports also, like for high side FETs. Q1 I have chosen, for Q2, for Q3, for Q5, for Q7. For each you have to generate the port. After that, click OK. Now your port will be generated. And another method is manual method. Just zoom, like somewhere you know that at this point I want to create the port, or at this point I want to create the port. So just zoom here. Okay, I was zooming here and go to the home tab, and this circuit element you can add capacitors, you can add inductors, you can add resistors. So here you can see that there is an add port option. So click on the add port. First point choose as a positive part. Second point will be as a reference part. So click here reference part, and it will show you that these are the positive terminals with the negative terminals. Click OK. Give the reference impedance. And after clicking on the reference impedance, click OK. And this will be your port created. Like I have already created the port, so I am here not creating, that's why I'm not creating the port. This is basically your port created after your like this a manual or automatic method, any method you want to be. So after that, this is basically our simulation where our setup is completed. Now setup is completed. Now we have to generate our SYZ parameters. So go to the simulation tab, and going to the simulation tab, we can directly compute SYZ parameter, compute resonant modes, whatever you want to compute here. Any results you want to see, you can see that. You can directly couple this data with the HFSS also. You can directly compute the SYZ parameters. So click on the compute SYZ parameters. Just define the values, like starting frequency, what will the starting frequency, and at each, like what will the distribution, linear distribution, bi-decade or linear step. And after that, just launch the files and run time predictions. You can see that there's the 4 cores, and under 5 minutes, this simulation will be completed, and approximately under 1 GB data will be used. And since this our 9.83 GB RAM is there in our PC, so 4 cores is needed for this our simulations. So this is our like memory predictions. So how much predictions, like how much time will be needed for these simulations, and how much memory will be needed. So for that, we will just click on the launch. I have already generated, so I will not generate here. Just double click here. You can see this data. So here you can see that this is basically, it is not much visible here. So I will directly export this in the Network Data Explorer, which is basically our post-processing result viewer. So here you can see that for each nets, we can generate the return loss. For each nets, we have generated our return loss, and changing, like if you want to go with the Y parameter, Z parameter, port impedance, you can check from here. And after this is where our first step in the presentation. Just a sec. This part here, you can see this part is completed. Now I will move to the circuit simulation. For circuit simulation, you need our workbench, which is basically Ansys Electronic Desktop. It is basically workbench for electronics. So clicking on that, so this is basically our electronics desktop. In this, you can see that these are all the tools here: HFSS, Q3D, Circuit, Emit, IcePack, Maxwell, Simplorer, Mechanical. All tools are there. So you can use this and couple each with the others. So I will just open my circuit. So this is basically our circuit where this is our input parts. We can directly couple this data. Just a sec, I will import my whole data. Just give me a sec. Because simulation will take few minutes, so I will just show you my simulated results. Yeah, so here you can see that this is our inputs. So these all resistors are imported from the SPICE models. And this is our component library where you can extract any components you want to use, like BJT, FETs, EMC tools also, like allies and networks or VRM models you can use here. And these are all the inductors, lump behaviors, or you can use the switches. So all things are there. These are all the switches, switching circuits. This is our from where we will take the output, and this is our PCB model. So when I'm importing the PCB, so just give me a sec, I will show you how we have imported this PCB, this PCB model itself in our this model. So directly here, right click, add subcircuit, add SIwave link, click on the add SIwave link, directly click on this 4-phase buck CE, open. So when I'm opening it, you in the when I was doing the simulation in the PCB. So in this, when I was checking the parameters, so here you can see that there are 31 ports. And when I'm porting my model here, there the number of pins 31. So it verifies that my whole data is extracted from the SIwave. So clicking OK, your PCB will be imported here. So I have already used here. So I'll just escape this model. So after that, I will move to the analysis part, and in analysis, I will just give what is my starting points and what is my stop points. I will give that. from 1 nanosecond to the 200 microseconds we are taking. Just click OK. We are doing the transient analysis. After that, we will generate the results. So our first result will be about the V input upon V output. So this tells you that from where our interference is happening. Like at this situation, you can see that this is going up, and from this situation, it is going stationary. So, okay. So this stable positions is basically tells us from there interference is there. Now I will generate the plot for our interference. So now this is how our noise is generated. So in this, we can't analyze at each position. So for that, what we have done is we have given a particular distance and particular situations. So now at each points, we are analyzing how much radiation is there, noise is there. And this tells you like how noise is calculated. And after that, we can also add limit line here. We can click on the add limit line, specify points, and import the data. Import the data sheet, and importing the data sheet will give you all the results. So this was basically a simple workflow how the conducted emission plot will be generated. And when I'm moving to the radiated emission plot, I will directly again, first I have to First, I have to click on my PCB. This is our PCB. Right click, push excite, and after clicking on the push excitations, currently it is not aware, but when the simulation will be completed, push excitation phase will be there, and when push excitation we will do, you will directly jump into the SIwave again, and going to the simulation tab, compute far field, again give all the data, and launch it. And when this data will be generated, your far field report will be generated also. So this is all from my side. If you have any questions, you can ask. This was basic, a simple workflow. In details, if you want to analyze, you can directly contact me over this mail. Just a sec. If you have any queries on other tools, or if you have if you want to go in detail about this, also you can directly contact me on this email, and I can revert back. I will revert back to you. You can take a screenshot also if you want.
Anybody has any questions, you can please put it on chat box, please.
So, Sargaji, I think I have resolved your query about the EMIEMC test which you are asking for. And in case, in detail, if you want to go through that, I can help you. I will help you on that also. Yeah, you need to assign the sources which are available in our available in our component library itself. Like in the circuit part, you can see that this is basically our source designs. This part is our source model. So we have assigned the source model here. So coupling it with the whole system, it is going with the simulation phases. So you can directly use these independent sources also here. Here you can see that these are the independent sources which you can directly use, or there's some this is basically a violation networks. So we have given a voltage source here. So you can use these sources also from our library, or you can import your if you have some spice model or any models, you can import those also.